Hello, hello, hello. Can you hear me? Oh, one bit. Hello, I'm going to say hello. Good afternoon. Hello. And does that, yes, excellent. We're back in business. Okay. It's been such a technological desert lately, or a hardware desert. Excellent, excellent. So, hello, hello. Good afternoon, Jamie. Hello, Mira. Yeah, Jamie. Oh, thank you for the feedback, Jamie. Hello, Alirat. Good afternoon, Angela. Good afternoon, direct message person. Um, oh, glad to see you, direct message person. Okay, more people coming. Oh, wait, sorry, just lost the chat. Where'd the chat go? Okay. Hello, Amale. Oh,
Good
hello.
afternoon, Professor.
Good afternoon, Layatule. Thank you for saying that with your voice, and thank you for showing video. That's a million points right there. I hope he submits. That's great. Thank you. And I'm still saying hello. Oh, but there he goes. Okay, but still, thank you. That's still a million points. I said hello, Amelie. Good afternoon, Alexander. Alex. Sorry. Okay. Good afternoon, Michael. Good afternoon. Okay, I think that's everybody. Is it? Well, also, I was just going to say, yes, good afternoon, Taco Rube. Thank you. Excellent. Oh, and I think, and Nathan, good afternoon. And Mira, did I say Mira? But anyway, I think, oh, yes, I did. Yes, I did. Okay, okay. So hello, everybody. And thank you, Nathan, Angela, and Layatule for showing an avatar. I appreciate it. Okay, we're going to get rolling in a second. Some announcements to logistics. Well, let's get rolling. Okay. You can see, you can hear. That's good. That's good. We have new hardware now. So this should be a lot better. Oh, and good afternoon, Yechon. And thank you for showing something other than a black box. And there's still more people coming in. Um, 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 um. This is kind of our rough agenda for today, is to discuss these equations right here, some of which may be familiar at this point. I hope. Maybe you write them slightly differently in lab. Good afternoon, Yechon. Thank you. Okay. Well, we're going to discuss. Okay. Good afternoon, Carla. Thank you. Okay, welcome. Oh, still more people coming. Okay. Pardon me. We're just going to get set here. Okay. All right. This is what I believe. Just some logistical things first, hopefully quickly. I believe. Okay. So everything with homework is still always like draft, back and forth, draft. Like, in other words, it's still never too late for you. As long as a portal is up, no matter where you are, it's never too late to turn in a homework. It is never too late to revise and upload another copy of the homework based on things we do in lecture. There is at least one of you. I'm not going to name names, but I am actually going to private chat for a second. Hold on a second. Hang on one second. And I know someone's here. Sorry. Okay, we're still getting rolling here. Okay, just to be clear again, since we only meet once a week and some things are still unclear, at any time, as long as the portal's up, it's never too late to turn in a homework. It's never too late. Oh, until it is. I mean, until I say so, but it's still not too late to turn in any homework. Ideally, you start them and you try them yourself before we discuss them. But then when we start discussing them, if you can do better on them, then you upload another revision. The more revisions you show, the more work you're showing you're doing. It's all fine. It's all progress. Each time you turn in a version or a draft, you get a number of points. You get more points as you go. Everybody can still get all the points on any homework. Of course, the faster you do it or the earlier, the less you fall behind, the better it is for you. But it's still not too late for anybody to hand in any homework that has been due, whether we've discussed it or not. If we have discussed something, you can still turn in a revision. But the same goes for me as well. That is, if you've ever turned in any homework at all, like, I believe that everybody who's turned in anything at this point has gotten something back, like some kind of points back. In some cases, people have gotten some feedback, in some cases not. But just remember, if ever you turn in homework if you get homework back and it's anything less than all of the points, just remember, if there is feedback there, then use the feedback to then get more points if you wish. All of this is like, none of this is mandatory. It's all to help your grade. If you never did a stitch of homework, but you got 95s on all the exams, then, and the lab, then you would have an A. So this is all for your option and benefit. But just to remind you how that works, if you ever turn in a homework and you didn't get all of the points yet, if and when you get feedback to tell you how to get more points, then use that feedback to hand in a revision and get more points. But at the same time, if you got a bunch of points, but you didn't get all the points, but you also don't see any feedback yet, then that doesn't mean you've done anything wrong. It doesn't mean there's anything you should or could do yet. It means it's an acknowledgement that you turned it in and you turned it in on time and that you're on top of the class material. But but then sooner or later, you're either going to get feedback from me to say, here's how you can get more points, or you're just going to get more points from me. In other words, again, if you have feedback and not all the points, the ball's in your court. If you don't have all the points, but you don't have feedback, the ball's in my court, and you're either going to get more feedback or more points next. Okay, I hope that's clear. So never be upset if you have less than a perfect grade on something, but there isn't feedback on it yet. Then just wait. You're either going to get feedback or you're going to get points. It doesn't mean you've done anything wrong. It means I haven't zoomed in all the way to the details yet. So just to say that, for example, on homework one person in the class has already turned in a whole new revision based on whatever we went over last time. And they got and it was beautiful. I was like very impressed. I'm not going to name any names, but I just want to acknowledge at least one person in the room has totally taken advantage of that. I mean, has properly used that situation and gotten all the points, and it's open to everybody still to do that. Okay, that's like how the homework is. So we have to still go over homework 2 that was just due today. Oh, sorry, I'm looking at the chat. I'm sorry. No problem. Thank you. No problem. Welcome. Okay, thank you. No problem. Okay, I'm looking at a couple of things in the chat. Okay, so now, it's always a little tricky in this double period because I feel in general, we have to go back and forth between trying to talk about homework and lecture material, but also trying to clarify or connect what happens in the lab. Like both of those are my job. So we sort of go back and forth in the emphasis. I feel like last time, thanks to some student feedback, we eventually went pretty full court press on going over homework 1. The very last part of homework 1 really is the underlying thing of all of your labs lately. So I have to expand on the last question of homework 1. And then of course that leads to talking about homework 2. That's like one of my main goals for today is the last part of homework 1 and to discuss homework 2. Just to be clear, homework 3 was, so of course, if you turned in homework 2, you'll notice it was due just like 5 minutes ago. So if you turned it in 5 minutes ago when it was due, then you've already gotten a bunch of points for it, for the fact that you made a reasonable, responsible attempt to try and turn it in. So you've gotten many points. You haven't gotten all the points because I haven't looked at the details yet. But again, the ball's in my court. You get my point. So, but of course I haven't looked at it because you just turned it in. Well, but thank you. And if you got a bunch of points already, that's an acknowledgement that you're on time and you're on top. If you still haven't turned it in, you still can. Okay, we're going to start discussing homework 2 today. We are, but I want you to notice too that the homework 3 that's posted, it actually starts looking like the practice version of like a big chunk of what the midterm will look like. It's a sneak peek, just so you see it. When you open homework 3, you're going to notice it looks like an exam. It is. It's an old version of an old exam, or it's part of an exam. It doesn't count as an exam. It's practice for you to practice for the exam. We're not up to an exam yet. We're not talking about an exam yet, but that will give you a very good idea of like kind of parts of what the exam look like. And you'll notice if you open up homework 3, it looks very long. It's many pages, but 2 things about that. After the first few pages, it looks redundant. You'll see already like a repeat of exactly what you just did for homework 2 here. That's not a mistake or a coincidence. That's because what you just did here sort of gets absorbed and involved into the exam. So by the time you get to homework 3, you're practicing again the same thing from this week that we're going to talk about. So I don't know if that's clear, but it's not a mistake. That's like practice for the exam. of course, in the exam, the numbers will be changed and stuff like that. But we'll talk about that when we get there. The other thing, though, is please notice that homework 3, because it is long and because we still have much to talk about, you have 2 weeks to do it. It's not due next week. There's nothing due. There's nothing new due next week. It's time to catch up and start preparing for this longer homework that's due in 2 weeks. So what I want right now, before I go any further, since I know I'm talking a lot and saying very little, and I know I'm talking fast, can I just get acknowledgement, if you hear me, that there's nothing new due a week from today? Like a week from today, you just catch up and start on. Okay, thank you, Caitlin. Anybody else hear me that there's nothing new due a week from today? Great. Thank you, Mira. Thank you,
Yes,
Taco.
Professor.
Thank you, Yachan. Oh, and thank you for voice. I just heard. Oh, thank you. I think I just heard voice. Thank you. Thank you, Ali Rot. And great. That's Jamie and Montserrat. Thank you. Okay. And if that voice was just confirming, then great. But if the voice was a question, definitely ask it. But I think that was just a confirming voice. Okay. Copy. I like it. Okay. Copy that. All right. So thank you all. Yes. Thank you, Jamie. Thank you, Michael. Thank you, Carla. Thank you, Nathan. And thank you those who did the Bitmojis. Now, here's another announcement. You're going to like this one that I'm also going to need confirmation of. Other reason I'm talking a little fast. I would like, to get to homework 2 today. I'd also like, if possible, to hear a little bit more about lab stuff recently, because we didn't really talk about that last week. But unless I'm checking something, unless I hear otherwise, wait, let me just make sure that I'm right. Yes, unless I hear otherwise, I'm going to tell you right now, and I'm going to ask you to confirm today. Yes, today we do have to end a bit early. We do have to end early today. I reserve the right, therefore, that I may post a short video over the next week or so. I'll either direct your attention to a video of not like a video of mine. I'll either direct your attention to an old video of mine where I cover some of this material, or I'll make a fresh video for you. I might do that. It depends how far we get to today. But today we're going to end like 45 minutes early, a little bit more than that. So like we're going to go more than halfway through this class. We're going to do more than a full period, but we're not going to do a double period today. We're going to end a little bit before 5. Okay, maybe like 4:45. So that's almost an hour early, honestly. So that's just on the edge of where I might be able to just make it up and happy news for you. But it's just enough that I may have to post a short video just so we stay on top of the material. If I do that, of course, you watch it whenever it's convenient for you, but just count it as the instructional time, please, or the curricular time that we will. So count it as asynchronous learning. As far as synchronous learning today, we are going to end around just about at 5:15. So you absolutely have the right, and maybe I'm even asking you to, like around 5:30, please feel free to politely remind me in the chat or however you wish that I have to wrap up, and we do have to end early today. We have to end around by 4:45. Am I saying that? I don't want to get false hopes up. Hold on, let me just think this through for a second. I mean, there's a small possibility that the thing I have to do will be canceled. Okay, here's the fairest thing I can say, because I don't want to mess with your minds, okay? Strongest chance is we have to end it an hour early, and please then feel free to remind me in the chat, like at 5:30 that we have to, at 4:30 that we have to end. Yeah, like pretty much we have to. Yes, Angela, what Angela's saying, I am saying, there's a little bit confusing. I make everything confusing, I know. I'm agreeing with Angela. That's pretty much when I almost definitely have to shut down. And you are welcome to remind me of that at 4:30. I'm going to ask for confirmation of this in a minute. But I'm going to say also, just to be totally fair and honest, the thing I have to do could be canceled. If it's canceled, and I find that out in the middle of this class, I'm not trying to mess with your minds. If it's canceled, I'm going to stay and keep teaching so that I don't have to make a new video for you or blah, 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 blah. But since I'm already telling you we're leaving early, if the thing is canceled and I continue to teach, if the thing is canceled and I continue to teach past 4:45, and I say that like, oh, I can stay, I'm teaching. Then I won't be insulted or upset if most of you leave because I'm telling you now that you're allowed to leave. Then I won't, but I will continue teaching anyway. And the point is then I'll teach for an hour. And even if almost all of you are gone, because I already tempted you with this early departure, even if all of you are gone, I won't hold it against you or anything like that. But then I'll continue to teach and I'll continue to record myself. So then I will just say, okay, once I've posted this video of today, remember, in that small chance that I don't end early, I'll just remind you, please, if you did leave early, it's no harm, no foul, but just watch the whole video so that you see the material. Okay. So I'm saying in summary, and then we're going to get rolling. Probably we're leaving early in an hour. Probably we're leaving an hour early, and probably please remind me of that at 4:30. But in the small chance that I don't have to leave early, I'm going to keep teaching anyway. And I won't be insulted if you leave, but I'm going to ask you to watch the video so that we don't miss the instruction. Can I get confirmation that you understand what I'm saying? Oh, thank you, Caitlin. That's one. Thank you, Carla. That's two. Are we okay? Thank you, Angela. Copy. Thank you, Nathan. Thank you, Michael. Thank you, Alirat. Thank you, Mira. Thank you, Madonna. Okay. This is like just weird enough. Is there anybody who's a little bit confused what I'm saying? Okay. Thank you, Sebastian. Oh, I didn't say hello, Sebastian. I don't think. Thank you. And Jamie, is there anybody who's maybe a little bit confused what I'm saying? You can tell me in direct chat. I know I'm confusing sometimes, but sounds good. Thank you, Echan. Okay. All right. Well, I'm going to, if you're all confused, let me know. But okay. But probably we're ending early. That's the bottom line. All right. Okay. So. That said, I'm going to start continuing going over the homework because I think that's probably the bigger concern. I'm going to hope to take a break in the middle and here. Well, no, okay, no, I take it back. Just very quickly. Can I get a quick sum from anybody in chat? A quick statement of what was your takeaway from lab 2 days ago? Like, oh, and in fact, I think it was 2 days ago. Wait a minute. This is that class. 2 days ago was a board meeting. Yes. You had a board meeting this week. Is that correct? In lab? Yes. Yeah. Okay, great. Okay. Ooh, that's good. Actually, so in some ways, I know board meetings are very funky. I'll ask a couple of concrete questions. Were you able, when you did the board meeting, were you able to move into another room, like into a proper classroom to do the actual discussion? Did that happen? Yes. Good. I'm very glad to hear it. Okay. I'm going to ask a couple more questions just because I know board meetings are weird for people in a way, although maybe in theory, some of you did them in 101, and I'll just admit to you right now, board meetings can either be amazing or terrible. I know that. They can be very awkward. I know that. They also can feel like you're not learning at all. I know that. They can feel like I'm not saying yours did. I don't know yet. I talked to Professor Moses for a long time right before it, but I didn't talk to him after it yet. So I'm just speculating from experience. I know that sometimes they can feel very non-productive. They certainly feel counterproductive when they're quiet and awkward for a long time. I'm not saying yours was. I'll hear in a minute. I also know that even when a lot of talking and debating occurs, a lot of times people end up debating and arguing about things that feel like they're going backwards in the material. I know that. And so it can feel to people like, oh my God, this is such a waste of my time. Why am I doing this? I sympathize with all of that. I will tell you directly from a lot of experience that even when they feel, especially when that happens, when like a lot of people are talking, but it feels like they're talking about old material or easy material or something, when it feels like that, to be frank, in the long term, it can actually be far more educational and productive than it feels during the moment, can be. Like I'm a big believer, when they work, they really work. And you don't always know what they're doing even while it's happening. Just saying. But now I'll hear from you. Okay. Oh, Okay, well, you're saving me time. So some of you, so I was just saying that to get that out there to sympathize with you, because it's not the last one you're going to do. And I'll even admit this too. The more you get used to them, or the more you find a way to like them under normal conditions, the more they end up being super productive right before exams, just saying. But okay, so I'm going to go with this. We're going to talk about this for a couple of minutes just because. So Ye-chan, thank you for saying, you don't have to be polite or whatever, but thank you. I'm glad that if many of you liked it, that's great. And again, I'm just saying, if you didn't like it, I understand if you didn't like it, but it may still be doing something for you that you're not realizing at the moment. But that's great, Ye-chan. So I'm going to ask a couple more questions then. So does that mean some talking did occur? You guys actually did eventually break the ice and talk somewhat? Yes, great. Thank you, Jamie. That's all. Yes, thank you, Michael. I'm really thrilled to hear this, because again, if it works at all, they're far more educated. I mean, look, if nothing else, at least it's not me yelling at you for 2 hours, right? Like, I mean, that cool. All right, so I'm going to ask a couple more questions then, since you seem with me. Thank you. If there was a debate at, we presented our answers. Good. Okay. Was there, great. Thank you, Ye-chan. Was there, well, here's the most concrete thing I can do for you, I suppose. Was there, cool. Thank you. And I hope you're not being polite. I mean, good. I'm glad. And of course, you don't have to be polite. Well, I mean, it's nice that you guys are polite, but like, I just so you know, I've been in situations before where right away in this day, people, in fact, even in office hours, I've been in situations where people were like angry about the board meetings and told me, and I didn't die or crumple over it. Like, I can take, you know what I mean? Like, but okay, cool. If you're saying positive things, I'm really glad to hear it for sure. So, let me, and by the way, I also, to be honest, when I was talking with Professor Moses the night before for a long time preparing it, we both were like, because he knows they can be really awkward at first. He knows that too. But we were like, if we have any predictions to make, we had a feeling that if it was going to work at all, it really might work with your group. You seem like the kind of group that could really get into it. So that's great. So let me ask this. Was there any issue that was like debated for a while that you argued over? And more specifically, was there any issue that you debated that you're not totally sure you resolved? Like, is there anything that right now I could maybe help you resolve more? Or do you feel resolved? I mean, so I guess I'm saying either two things. One, let me know right now if there's anything that isn't 100% resolved or clear in your mind, like it's still a little bit debated. Or if not, you could just let me know in the chat right now, like, what do you think the takeaway was? Like, what was a big concept that was resolved? And if I even get either one concept that was resolved or one concept that you need help with right now, I'll be like, that's good enough for me. Like, I'm saying, I'd love to hear either like anybody in the chat or in voice, just tell me either one concept that you're not totally satisfied with that came up, or one concept that you feel like landed, that you resolved, that you're glad that you got clarity on. Either way. And as long as I get one, or should I repeat the question? I can repeat the question. Hold on a second. So what I'm looking for is, if anybody in the chat can either summarize for me a concept that you feel like you got sort of clarified. I'm not testing you. It'll help me teach you better if I know. That's all this is. So either tell me one concept that sort of got clarified and emphasized, and even if you feel like you already understood it, if you just want to report for the class, a concept that either got clarified or, I'm seeing direct chat. Okay, cool. Okay. I'm looking at the direct chat. I'm not necessarily going to read it out loud. I might, but definitely helps me. Well, actually, I am going to read. I'm not going to say the person's name, but one person in the chat has said, actually, wait, you know what? I want to wait for one more. Just give me one more. I don't care if it's private or public. Either your view of here we go. Oh, okay. Interesting. Okay, well, the good news is what the two people in the direct chat are saying definitely relates to the homework we need to go over now. So that's good. Huh. Okay, okay, I'm just going to read. This is good enough for me, and I'm going to use this to jump into the homework because it sounds like we're on a good page. One person saying getting the last problem without using the unit circle because every group had used Google to look up the unit circle. That's very honest and very, very helpful to me. I'm a big fan of the unit circle, but I'm also a big fan of understanding things without having to look at, oscillation using, okay, this is great. Okay, this is perfect. So one person said that about unit circle, I hear you. Then another person in direct chat said about setting calculators to radians instead of degrees. I hear that. I really hear that. And honestly, I will tell you, I know technically this is all a review of pre-cal or trig, but I will tell you in my experience, secretly, one of the benefit, just like certain physics classes that require calculus actually secretly end up being the place where people actually start understanding calculus for the first time, even if technically they were required to. We always require all this math for physics, but the truth is for many of us, including me, it really should go the other way around. I really never understood or even liked the math until I started seeing it through a physics lens. So in some classes, they require calculus for physics, but it turns out they kind of end up learning the calculus in physics. And similarly here, just so you know, technically, I know you were all required to take trig or pre-calc, and you were required to learn about radians and the unit circle before this and cosine and sine. Honestly, in my experience, a lot of people end up really, one of the benefits I think of physics 102 is actually it becomes a place where a lot of people actually start really understanding what a cosine or a radian is for the first time. I didn't understand. I mean, I could memorize them. I could like do stuff with them, but I didn't understand them at all until a certain level of physics. So so I'm speaking to all of you right now, and then I'm going to read the last chat and we're going to go on. Any of you who feels at all rocky at all with radians or sines or cosines, and when I say rocky, I mean, I'm guessing that there's some of you in the room who can like solve problems with sine and cosine, who got used to following formulas and doing things or setting their calculator in radian mode. But there may be some of you who know in your heart that you've been like doing stuff for math professors, but you don't really like, but it doesn't mean anything to you. Maybe if you're like me, there was a stage in my life where I could do those things for a math professor who asked, or a math teacher asked, but I didn't really like it. It didn't mean anything to me. I could like do it, but I was like, whatever. This is just like black magic. I'm just like following some procedure. I don't see what's interesting about it. No one's even attempted to show me what's interesting about it. I don't see what's useful about it. I don't see what's pretty about it. And I don't get it. I'm just doing it. If you feel that way at all, I'm sort of hopeful that maybe some of this physics we're about to do might make it come alive for you a little bit more, maybe. So even if you think you can do it, I think there's still room to get something out of this. And those of you who in your heart are like, I've never felt comfortable with sines or cosines, like I just gutted my way through and I'm glad I'm done. Well, you're not done. We totally have to deal with sines and cosines and radians here. But take this, do not assume. One thing to take away from the board meeting, and then I'm going to look at the last chat and go, one thing to take away from the board meeting is we do not assume that just because you've been there, done that, with radians, sines, and cosines, that you've been there, done that. We do not assume that it's just like over. We need them now. We need them for this course. And we're not assuming anybody is a master just because they've seen it before. So all of you can take this as, including today's lesson on the homework. This is like a fresh opportunity and to get a fresh perspective on what radians really mean, what sine and cosine really mean, and specifically why they have anything to do with physics. In fact, I'm going to go one step further on that. What's the point of all this homework 2 or the last bit of homework 1 or all this? What we're really trying to show all of you in a way is why these weird things that you learned about circles back in math class, when you learned weird things about circles like pi and sine and cosine and radians, why any of these circle things would have anything to do with something going back and forth in a straight line, like a mass on a spring. That's the actual ultimate focus of all of this, is why are we using the mathematics of circles to describe the physics of something going back and forth in a straight line. That's the focus of all of this, whether you think you got it or not. And the ultimate answer is because something that's going back and forth in a straight line is moving cyclically. And we need the math of circles to describe the physics of cycles. That's what all of this radian and all this cosine and all the sine stuff is about, is using the mathematics of circles to describe the physics of cycles. Okay, that's like the focus that we're going to get to now when I go, okay. So that's what I'm going to get to. I'm going to turn the page in a moment and get to the homework, but I'm just looking at a couple more comments in the chat. Ye-chan, who went public. Thank you for going public. Is a review. Oh, right. So exactly on Ye-chan's thing, maybe that's what was in my mind when I was just talking. Right. It is like technically a review of pre-calc or calc. But how it relates to oscillation and and how it relates to labs 1 to 3, right, is confusing. So that's sort of my job here today, hopefully, is to address that, hopefully. And you could tell me as I go whether I am or not properly addressing it. And then there's something in the direct chat. Math. Cool. Well, at least one person in the direct chat feels like maybe math is easier to understand in physics. And, again, for me, that's true. I mean, I've always, it's so weird. We always require all this math to do physics, and everybody thinks math is like the necessary ingredient for physics. It just as easily could go the other way. And I was that person. I love calculus now. I love trigonometry now, but that wasn't initially true for me. It's because it came alive in physics for what it's worth. And I didn't, anyway, so it can go either way. Yes. Okay, that's very helpful, everything you guys just said. You could still add more. You can say more about the lab if you want. I don't want to pull teeth. So what I think I'm going to do, I'm going to start. Okay, I'm going to go back briefly, hopefully briefly, to homework 1B, or I think it was called homework, the very first homework, the thing on the spring business, the very last question. If I recall correctly, and correct me if I'm wrong, if I recall correctly, we had this thick class last time where we went through all this material, and then I got to the very last question and I said the answer just to leave you with some sense of closure, but I didn't really explain where it came from. And it really is the centerpiece of everything you're doing in lab right now. So unless I'm wrong, I want to go a little bit more slowly and expansively over that last question, and then it'll lead us to homework 2. So what we had again, we had this. Right, and we had these facts. Those were all the facts, right? Yes. Okay, there were those facts. Okay, and then question. So technically, again, if I were doing homework right now, or for an exam, all of this technically up here is step 1, diagram and fact pattern. Right, and now technically step 2, what is the question? Would be the question of question 9 was at t equals 1, what is x, right? That was the question. Okay. Now, before I even go to step 3, I want to that's technically the question, and stop me if I'm wrong, but that is technically the question. At t equals 1 second, what is x, i.e., where is the mass in 1 second into its motion? And we know the answer has to be somewhere between 0.15, and I should do this too, and 0, right? It's or excuse me, it's got to be somewhere between positive 0.15 and negative 0.15, but it can't be anywhere outside of that. And just to remind you, we decided to call this the positive direction and this the negative direction. But I want to rephrase this question slightly now that we're relating it to, since this was originally just like a homework, but it relates to all these other physics applications. Like you've done like 3 labs already or so, or 2 or so labs that all kind of relate to this type of motion. So it's not that I really am ultimately so concerned with exactly where this particular mass is at exactly 1 second. That's not really the issue. The real question here is, given a mass on a well-behaved spring, right? Given a mass that obeys Hooke's law, and of course, given what's always given, which is Newton's second law of motion, given those constraints, the real question is, what is x as a function of t, right? That is really the question. In other words, in order for me to find out what x is at t equals 1, what I'm really looking for is some kind of expression or equation, or what you might call formula, although I hate that word. I'm looking for some kind of relationship, some kind of ultimate function, such that you plug in t as an input and it will spit out x as an output. Like, to be blunt, if we literally already had an equation for this, if we could just look up the equation from physics 101 or something, if we knew it was like x equals 1/2 at squared plus v naught t, in fact, I'm going to write this, so I'm just continuing. We want to know x equals function of t, right? An example of an x function of t would be x equals 1/2 at squared plus v naught t, like plus x naught. Like, that's an equation from physics 1, right? And I'm just trying to be clear. I'm not saying that's the right answer. It's like totally not the right answer, but I'm saying that would be an example of an x function of t, meaning that would be a case where t is treated as the independent variable, right? The input, so to speak. And x would be treated as the dependent variable, the output. And that's what we're looking for, some kind of expression like that, where you plug in t and what comes out is x. We need something like that. If we just knew it, if it were x equals 1/2 at squared plus v naught t, we would just plug in 1, the value 1, and out would come x, and that would be our answer, right? We need something like that. But as I think I mentioned last time, or I think it mentions in the sheet, this would be an example, but this example does not work here. Does not work here. What do I mean it does not work here? Well, that is an example of an x function of t, but it's not a good example. I mean, it is an example, but it violates f equals negative kx. Because, let me write this in a different color. It's confusing. If f equals negative kx, and if f net equals ma, then f is not a constant and a is not a constant. Maybe I should write that bigger on the next page. Yeah, I'll write it bigger on the next page. Okay, I'm saying, and you could tell me to go back. Tell me to turn back if you want. Here, f equals negative kx. And of course, f net equals ma, i.e. negative kx equals ma. So a is a function of x, right? A changes as x changes. For every different position, there's a different instantaneous acceleration. Therefore, a is not a constant. So we cannot use, I'm just reminding you why, we cannot use x equals 1/2 at squared plus v naught t. Right? Okay, like if you wrote down x equals 1/2 at squared plus v naught t plus x naught on an exam or something as a GDP, as a step 3, it would be true. It's true. It's a great statement. But it doesn't apply here because it assumes some value of A, some constant value of A that you would plug in. What would we plug in for A? We don't have one constant value of A here. It changes all the time, right? So we cannot use, we cannot use that. I'm saying all that just to say, so what we're looking for, again, the big goal here, what we really are seeking here is some kind of X as a function of T, something that has that kind of format as that equation, but isn't that equation. We need a new one. So last thing I'm going to say about this, why am I making a big deal? Once upon a time, we might have thought of physics as if you get a problem in physics, you pick the correct equation, you plug into the correct equation, you get the correct answer. What we're seeing now, especially in lab, is that the job of a physicist is not to plug into equations. The job of a physicist is to come up with equations. That's what you're doing in lab. That's why you keep testing different motions, what we're calling motions, and seeing if they're true or false. And here, this is like the homework version of a lab question. Can we come up with an equation, a relationship, a function that fits the conditions of the situation? Okay, so right? So the reason that you do these things first in lab and then we talk about them in homework is that we're literally asking ourselves here to come up with a new equation, X as a function of T, given F equals negative KX and F equals and F equals, sorry, and F net equals MA. So I'm not trying to depart from the homework. In fact, to sticking with the homework, and again, you can tell me to go back a page if you want, but our step 3 GDP, the thing that we know, what we know, I mean, I already wrote it before, but we know that F net equals MA, and we know that F equals negative KX. So we know that negative KX equals MA here. One second, I'm sorry. Okay, and I just got confirmation. We are going to end early. Okay, that's just a confirmation. So you can remind me at 4:30 to wrap up. But okay, this is what we know. Negative K, can you even see me? Okay, negative KX equals MA. I'm just okay. So we know that. Do we know anything else? Well, we know from the lab, we know and when I say lab, I mean now lab in general from the last 2 labs, I believe. We know I'm just going to change the view of the screen. Okay. We know that if you treat t as the independent variable, and you, like t as in time measured in seconds, and you treat x as in position, displacement from equilibrium, measured in meters, you know that if you start the mass at some initial position, call it x naught, right? And I don't care whether x is measured like this or x is measured like this, right? X is just whatever one-dimensional axis your mass is free to move along, right? So like in your first lab, I believe your masses were on vertical springs because frankly, that's just easier to play with and easier to measure. Where however your springs were oriented, we're treating x as the displacement in space variable. We're treating it as the dependent. We're treating time as the independent. Well, you know, if you started the mass at some position and you let it go, it started coming back to the equilibrium position smoothly and faster, right? Like slowly at first, but faster and faster. So unsteeply at first, and then more steeply as it went. And then it passed through the equilibrium position and then kept going and then slowed down until it stopped at a point equidistant on the other side, right? And then it started coming back and going up toward the equilibrium position faster and faster until it slowed down and kept going like this, right? Like if you took data, especially I think this was, well, I can't remember which lab it was, but if you took data, or quite frankly, and this is another way physicists think, you did a bunch of different labs now. You've done a bunch of different curve fits and a bunch of different relationships, but you've played with the idea is that you've played with oscillators, masses on springs, and maybe even pendulums too, enough that even if you're not right now, anybody I'm talking to, anybody who's still with me, even if you're not literally looking at any of your sheets from lab, you were in the lab enough that you can picture this thing going back and forth or back and forth and back and forth. And I think you would disagree, hopefully do disagree with me in the chat if you disagree with what I'm about to say. But I think if you are in the lab enough and pictured and watched things going back and forth on an elastic material, then you can even see in your head that this is the way they went back and forth, right? Again, now let's be clear. Nobody is saying that your mass curved. Like the mass is going back and forth in a straight line, or back and forth in a straight line. But if we were to make a graph of where it is in that straight line as a function of time, then the graph is curvy and repetitively curvy. Why curvy? Because it's smooth, because you got something that's going back and forth. And what it's not doing, I mean, and again, disagree with me in the chat or question me in the chat, please, if any of this is unclear. But I'm saying, even if you're not looking at any of your lab notebook right now or any of your lab data, if you are in the lab at all watching, you ideally can picture in your mind that what I'm drawing here is, is a sketch. Of course, I'll make it a little bit better. It's a sketch, but I hope you would agree that it's a fairly accurate sketch of the XT situation, and it goes on and on forever. Why? Because I'll even be more, because really that's the simplest possible way to, oh, it does. Oh, okay, great. Someone in direct chat is saying it's making sense. Great. And I'm going to go a step further. And again, I know that some of your graphs were different. I know that you did like time as a function of, I know you've done many different graphs. And so something that's, and this is just a sketch, but notice the requirements of a physics sketched graph. It's just a sketch, but it's very informative. It's very informative. It gives a clear sense of the relationship and the scale, as long as my axes are labeled and at least one significant point is labeled, right? Some of your graphs I know were horizontal lines. I'm aware of that. I mean, that's very good. And even some of your graphs, if you linearize things correctly, some of your graphs are straight lines, but those had different axes, right? If you picture these axes, there's two things in the chat I'm going to check. If you picture a graph either literally that happened with these axes or in your mind what it would be, I think you would agree that you've got, and I'm going to look in the chat in 1 second. The real thing I'm saying is, even if is that the simplest possible way something could go back and forth in time would look like that, like what I just drew in red. That would be the simplest back and forth cyclical motion. But there's no way that you ever found a graph in lab that looks like that. Because if it was straight lines like that, like that's too simple. That would never happen in nature. If it was straight lines, that would be something moving at constant velocity somewhere and then stopping instantaneously like a cartoon, right? Like if those are straight lines, remember from Physics 101, the slope of connecting 2 points on a position time graph, the slope is the velocity, if you recall the average. So if those were straight lines, it would be something going at like 30 miles an hour this way, and then in like no time at all, completely coming to a stop, and then completely heading in the other direction in no time at all, and then going in the other direction at 30 miles an hour, and then going, and then doing it again and again. No way did that happen in the lab, right? At best, if you got any kind of data at all, you had something that was going, slowing down, and then turning, like slowing all the way to zero, and then speeding up and passing through and spin, slowing, going down to zero. And that, right? I.e., it has to be curved for it to be smooth, natural, actual motion. Things have to slow and speed up and slow. So that, I believe, this is what you would have or did or would see in the lab if your input, if you made a table of values where time was your input and position was your output. That's what I'm claiming so far, but I'm looking in the chat because at least two things are happening in the chat. Sorry, hold on. Oh, cool. So two people privately said that basically, yeah, there's sort of, well, one person said makes sense, and one person said they sort of have a pattern to their movements. Yes, I think there's a pattern, meaning a repeated cycle. And every time I look at my drawing is terrible. Sorry, but yes, it's supposed to be a repeated pattern. Absolutely. Sorry. And again, stop me if you want more, if you in any way, but I think that's what you would see or did see if you made if you threw data into that table of values and put that on Desmos or Logger Pro or Excel or whatever. Now, where am I going with this? Well, the way physicists work is they throw their data into Desmos or whatever, they get a scatter plot, and then they try to think of what is an expression, a mathematical relationship that we already know that comes closest to, or what's the simplest, well, that's the question. What is the simplest mathematical expression we know that best captures this shape or this trend? And I guess I'm just going to, I think, like that shape that the data more or less falls into, and of course it doesn't fall into it perfectly, but it most closely falls into that shape. What is that shape known as in a math class? Like what function? So I am actually asking you now. I mean, you totally know this because all the homework is all about it and all that, but what is the mathematical, whether you like the mathematical expression or not, just what is the mathematical expression or the mathematical function that best captures this shape? And I am asking. Okay, so there's one person in the direct chat that's, first of all, at least answering my question. Thank you, person in direct chat. Okay, I'm now getting two answers in the direct chat, and I'm very pleased. At least two people in the direct chat are certainly showing that they're paying attention. They're certainly showing me that they hear my question, and they're also helping me teach. I will say that both the people in the direct chat, actually, the answers are, to be honest, they're not correct, but that means also, remember, you can submit for a bajillion points now, please, and I'm not being sarcastic. because you both had the guts to actually say something about this and show you're paying attention, there's at least 3 portals that you can submit those answers into for a lot of points. And one of the portals does say be wrong, be really wrong, because honestly, I'm admitting that they're not right, but it also shows me I'm not wasting your time by trying to teach this. Okay, now I just got another thing. Oh, sorry. Oh, one of them was in the public chat. Okay, so I'm going to maybe open up a new portal for just the guts to go public. Sorry. So I am going to admit parabola is, it looks like okay, you know what? The centerpiece of the whole thing, if I covered, oh, I can't. If I covered up the 2 other humps and you just looked at the hump in the middle, you're right. That is an upside down parabola. Just in the middle, that would be like x equals negative t squared. That is very good. But the truth is parabolas can't then start repeating themselves like the way this does. This is a cyclical kind of function. A parabola would just, a technical parabola like y equals negative t squared would just keep going. So it's a good guess, but it's not right. Now I am seeing in the direct chat, at least one person is saying the thing that I'm looking for. And I'm gonna push a little bit further. I'm gonna wait for one person is saying something that I'm looking for. And I'm going to wait till at least one more person does it too. And yes, it's a function that is all over the homework and that you've talked about. But I'm going to challenge the one person who's in direct. So it's not a parabola, okay? And it's not exponential. Exponential is a very good guess for another reason. It is a very good guess we might ultimately see. There's a lot of similarities to this and an exponential, but even an exponential also would not be cyclical like this. It would just go up or down forever. But it's still a very good guess. One person in the direct chat is saying something that's correct, but I'm going to challenge that, and I applaud that person. And he or she should also submit for points. But now I'm going to challenge that person, if I may. I'm going to wait for one other person to confirm or deny what's in the direct chat, but I'm also going to say to the one person who does have something correct, like he or she is naming the correct function, but I'm going to challenge and say, in a math class, you might say something like y equals blah, 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 blah of x, and that would be correct. But here, let's try to shift our perspective to physics. Here, the dependent variable is x, and the independent variable is t. So we want to phrase it that way. So I'm sort of specifically saying to the one person who just did something correct in the direct chat, maybe you can rephrase it as a t as the input and x as the output. Maybe, but if not, no worries. But not anybody else. I'm going to wait. I want to hear at least one other person in the direct chat. Like, what is a function you know from math that someone just wrote periodic function. It is a periodic function we're looking at, but yes. But now, can you name, like, periodic is like a description? Name a function that you know from math that is periodic. And by the way, again, guys, like, this is good. Okay. Now we're talking. Now I see it. Thank you, Yachan. And I did see it in direct chat a minute ago. And cool. And direct chat person that I just challenged a moment ago. Thank you. Yes, you totally nailed it. Thank you. And give yourself points for that. Like, that's like 3 more portals. Okay, now we're talking. Okay, now people, and this is good feedback because I also now know we're on the same page, but I'm also maybe not wasting your time, because here's what I'm seeing in the public. And thank you, everybody that participated. Please submit, like, really pat yourself on the back. So here's the thing, like I think Yachan publicly is very nicely summarizing what a lot of people are talking about in the chat. It's someone. Oh, I'm so happy. All right. I don't have time to, I'm not going to like type to everybody individually, but here's the deal. So Yachan is right when he says sine or cos. It is one of those. That is what I'm looking for, sine or cos. That doesn't mean we all fully understand what they mean, but yes, that is what we're talking about. Second of all, I'm going to say, because we're talking about physics now, we're talking about either, I don't know, can you hold that question for a second? I think it's tentatively in the Google Classroom. Fair question, but I'm going to get myself distracted now if I try to answer it about the exam. It's at least in 2 weeks. It's not for sorry, but it won't come as a surprise to you. I promise that we're going to be talking about that practice exam before we even have the exam announced. You'll have at least a week between the time that we actually start reviewing and going over that practice exam versus when you take the real exam. So it's not for we won't just spring it on you. I promise. but I just can't like track it right now. And I think a tentative date. Okay, now, okay, back to the chat. First of all, yes, it's either sine or cosine. Very good. Second of all, okay, now you're saving me time. Great. All right, I'll just get to it. Second of all, yes, it's either sine or cosine, but I do have to, and people were putting different things in the chat, and that is a legitimate question. Is it sine or cosine? They're so similar, right? But indeed, I'm going to agree with Yechon's and Madonna's most recent input that this, as it's drawn, seems to be cosine to me, or at least cosine would be the easiest, fastest, simplest way to describe this. I could technically tweak a sine to make it work, but with the least work possible, cosine captures this for exactly the reason that Yechon and I believe Madonna and others and people in the direct chat are saying it's a cosine because, and let's start with this. If you're going to memorize any, well, okay, yeah, I'm going to start by saying the answer to this, yes, the answer is some kind of cosine of t. Now notice I'm putting some blank spaces in there. We're going to get that to in a minute. I'm just saying the basic shape, the shape is cosine. Yes, that's awesome. Also notice I'm saying if you were in a math class, you might say y equals cosine of x. But here in this situation, I'm saying x equals some kind of cosine of t, right? T is the input, x position is the output. So it's some kind of cosine. The shape is cosine. And yes, how do I know it's cosine? Well, here's something. Yes, if you know your unit circle perfectly, then you would know this. But I understand you have mixed feelings about the unit circle. If there's one thing from trig that you want to memorize, because we all know sine and cosine are totally related and totally similar, but like they're different and they're easily confused. And people sometimes remember like, oh, is the cosine of this one a half or is the sine of that one a half? So the one thing to memorize, if you know that all of cosine is based on sine or the other way around, but you just don't know which one is which or whatever, the one thing to memorize is this. Okay. The one, oh, wait, I'm looking the chat. Right, Madonna, exactly. And what Madonna said last in the chat totally agrees with, or is like another good way of putting what Yechon said, which I hope I'm pronouncing correctly, in the chat. And here's the one thing to memorize. I mean, I'm writing it proper. I wrote sine, super, cosine, counterintuitive. The way I really say it in my mind is I always say, or you could say sine sensible, cosine counterintuitive. What I really say in my mind is sine super, cosine crappy. I mean, I'm not going to put that in paper, but like, and what do I mean by that? I mean, sine is what you would make if you were forced to make up a function while you were living on a desert island. You would make up sine. Sine is totally sensible. It's super. It's straightforward. Sine is straightforward. That is when the angle is 0, the sine is 0. And as the angle gets bigger and bigger, the sine gets bigger and bigger. It's like the one that makes sense. Sine, I mean, of course, it all makes sense in the end, but initially in your gut, in all of our guts, sine makes sense. Sine of 0 is 0. It's like all about the S's. It's like just be a snake and just make a bunch of S noises, right? Sine of 0 is 0. And then as the angle gets bigger, sine gets bigger, just like we would all want any function to do. It's cosine, that's the reverse of that. Cosine of 0 is 1. And then as the angle gets bigger and bigger, cosine gets smaller and smaller. Right? Now, I think that makes sense if you picture a unit circle. If you always picture that cosine is the x coordinate and sine is the y coordinate, well, then it makes sense if you start over here as you're going up and to the left on the circle, the sine values are going up, the cosine values are going down. Like once you start picturing the inner circle, I think it all makes sense. But ultimately, if you're going to memorize anything, if you're going to base your reasoning ever on anything, sine is your anchor. Sine of 0 is 0. If I were to memorize anything from trig, it would be that, because it's also, I think, sort of easy to memorize. Therefore, Yechan and Madonna and others and private chat people are correct. Like if I see a graph like that did not start at the origin, if the output wasn't 0 for an input of 0, then that's cosine. And let me tell you that physics-wise, our oscillating system here, our mass on the spring, it's always going to be like this. Like the whole point is you start the mass somewhere other than equilibrium and you let it go and it will start moving toward equilibrium. If you started at equilibrium, it ain't going to go anywhere. You're not going to have anything. So it's just going to stay at equilibrium. So all of these oscillators always start somewhere other than equilibrium, so they're best captured by the cosine function. So I agree. We're talking about, so from here on in, and remember, all of this, I know I'm talking a lot. Surprise, surprise. What I'm talking about here is homework 1B, question 9. What I'm really talking about in general is how do we predict I'll just remind you, what we're really talking about in general is given an oscillator, given something that's moving periodically or cyclically, how can we predict where it's going to be at any moment in time? That's always a physicist's job. You name the time, can I name the space? Like that's the physicist's job. Can we predict where something is going to be when? Well, the predictor for an oscillator is going to be some kind of cosine function. In fact, that's really what a cosine function is. It's a cyclical function that predicts cyclical behavior. So we're getting some, okay, so the answer is going to be, okay. So what we've established so far, I'm looking at the time. Oh, we're good. Okay. What we've established so far is that if we're going to be able to predict the behavior, and again, this is what we're talking about right now. In theory, is the last question on homework 1, but it's really like everything we're doing for the first like month and a half of the course. We're really talking about oscillation. We're talking about a particle undergoing cyclical repetitive motion that's called oscillation. And what we're trying to do here is come up with a mathematical way to predict and capture the physical motion of oscillation. Like that's our job. And that's what anybody would ever do in a physics lab. Like you've got some type of behavior. What's the mathematical functional description of it, right? So what we've established so far is the basic shape, the basic function that we're going to use to describe oscillation must be a cosine function. Some kind of cosine function, some kind. I.e. what I'm saying is the big picture answer here is cosine, but I think there's details that we still have to fill in. When I say, what do I mean by some kind? I mean, there's details that have to be fit in because this is science. This is about measurements. It's not just raw math. So Okay. The reason I keep writing, so cosine, we've established it's cosine, but I keep putting these blanks around the cosine for a reason. Because like x equals cosine t is a perfectly valid abstract mathematical function, but we're not in abstract mathematics here. We're talking about actual measurements. We're talking about reality. I mean, no offense, some of my best friends are mathematicians and some of my favorite places aren't reality. But if we're here in measured empirical reality, we're measuring these values and we're measuring them with equipment that spit out units, right? Like we have to care about units of measurement. So let's look at that. So let's look at that I'm going to go backwards. Let's look at that blank right before the T. There's got to be, the reason I'm putting a blank there, there's got to, well, I'll write on it. I'm claiming right now, and I'm about to turn the page, that there's got to be something multiplying that T, and there's got to be something multiplying that cosine expression in order to make the units make any sense at all. What I mean by that is T is time measured in seconds, but you can't take the cosine of a second. Cosine is not a function that acts on seconds. As you know from math, as you know from, I guess, your board meeting, I think, and as you know from having tried homework too, like cosine is something that we do to angles measured in radians. Now, what angles measured in radians have to do with this, I don't yet know. I mean, I know, but we may or may not be comfortable with what angles and radians have anything to do with this thing, with a mass going back and forth on a spring. But we do know you take the cosine of an angle measured in radians, right? You don't take the cosine of a time interval measured in seconds. So I'll write it. Okay, I'm going to be careful about this now. So what I'm saying so far And again, some of you, this is already obvious, and some of you, this is already confusing. And maybe there's one of you that's right in the middle and I'm talking to you. But like I'm saying, you can't take the cosine of seconds. You can't. You can only take the cosine of radians. So in order for us to apply cosine at all, we're going to have, for there to be any function that makes any sense out of your data, the function that we're looking for must first multiply the seconds by some number or some constant that is measured in radians per second, so that the seconds cancel out and we're left with radians. There's got to be something before the t, right? So that we have radians per second times second, and the seconds cancel out and we're left with radians. So there's going to be something before the t. I don't know what it is. I just know there's got to be something measured in radians per second. So I'm going to give that constant. It's a constant, but I don't know what it is. I don't know its numerical value. I don't know anything about it yet. I just know it's got to be there. It's not a variable. We already have our variables, input and output. So there's got to be some unchanging number that always multiplies by the t to cancel out the seconds and leave us with radians. Okay, so I could call that number whatever I want. I don't know it yet. I could call it x, but I'm not going to call it x. First of all, we already have an x. Second of all, x sounds like a variable. This is not a variable. It's an unknown constant. So I could call whatever I want. Don't be intimidated by the name. But I've run out of letters in the English alphabet, let's assume. So I go to the Greek alphabet just because, and I picked it. And so okay, that's a lowercase omega. Okay, I could have been anything. Don't be intimidated by that. It's just a name. Like literally, I could have called the thing X or Yaverbaum, but I'm calling it omega because that's what everybody else does, right? So what do I know about omega so far? I know that the units of omega are radians per second. That's all I know so far. You may or may not be comfortable with radians entirely, but again, that's sort of what your board meeting was about. And I'm going to make you more comfortable with them, I hope. I may also shove them down your throat so much that you hate them even more by that. But we're going to talk more about them. But whatever radians are, which is some kind of measurement of angle, right? Omega must be measured in it per seconds. So far I have thus far we have x equals blank cosine omega t. Okay. Now, again, what is omega? We'll talk about that in a minute. All I know right now, it's a placeholder for some kind of radians per second that will cancel out the seconds and then allow me to take the cosine of something as long as my calculator is in radian mode. But before I discuss more about the radians per second, what's going behind, in front of the cosine? Well, this is easier. Honestly, if I've lost you a little bit with the radians per second, bear with me. And this next part will be a similar kind of argument, but maybe a little bit easier to follow. Cosine only spits out numbers between 1 and -1, right? Like the biggest cosine, like the output of cosine is always some fraction, some decimal. Oh, someone's here. Sorry, hold on. Right? It's always like a fraction between -1 and 1. And that's a weird symbol. What I just wrote at the bottom, hopefully you're following me. Like it looks like, what did I just write at the bottom? And bracket cosine omega t, bracket equals bracket blank, what am I saying? Well, please note at the top here, if I've never made this clear before, whenever I use square brackets, I'm talking about units, right? If you look at the top, and you may want to make a note of that in your notes if that's not like a thing that you're used to. At the top, when I wrote brackets around omega and then brackets around radians per second, I was saying the units of omega are radians per second, right? Okay, so please make a note if you're not, that whenever I use square brackets, I'm talking about the units of something. So what are the units? And now whenever I say omega t, right? Like this is, you could, in your mind, you could substitute X if that's what you're used to for math class, or you could substitute theta. Like omega t is now a quantity. It's like a quantity measured in radians. Like it was something measured in radians per second times something measured in seconds. So it's like, so the seconds canceled. And now that omega t is like a little quantity in itself that I'm taking cosine of. Well, whenever I take the cosine of anything, what do I get? I get a number between -1 and 1, right? And what I get is literally just a number. What I'm writing with the brackets at the bottom here is that the units of what gets spat out when I take the cosine of something, the units that get spat out are no units at all. Like, what am I saying? I mean, for example, you know from math class that, I'm not going to test you right now, but I think this will be familiar. From math class, the cosine of pi/3 radians, or what, if you don't like that, the cosine of 60 degrees, right? We're not in degrees here, but I can convert just so we can relate. You might remember from math class, the cosine of 60 degrees. Actually, I'm going to ask, we've got a minute. I'm not quizzing you. I'm not putting you on the spot, but just to make sure we're still together, does anybody in the chat want to write? Do you think you remember what the cosine of 60 degrees maybe is, or shout it out if you want, just as a little refresher? The cosine of 60 degrees, it's not a quiz. I'm just wondering, the cosine of 60 degrees. Does anybody remember or want to take a guess? I'm going to say it again. I'm going to wait till I get like 1 or 2 things in the chat. I don't care if they're wrong, and you actually get more points if they're wrong, remember, which is weird. I see 2 things in the chat, and at least one of them was public. All of them were public. That's so gutsy. I'm so proud of you people. 3 people went public on this. And by the way, the 3 people who went public were all correct. Yo, that's awesome. I'm totally opening up a new portal for going public. Yes, the cosine of 60 degrees is 1/2. Now, they're strictly, so yay, first of all, yay, and your math teacher thanks you. Yeah. Oh, thank you. And thank you for the reminder. That's 4:30. Okay. And again, thank you for the reminder. I appreciate it. And that is a reminder. Like, I'm going to start winding down here. Luckily, we are actually almost where I want to be. We're going to shut down at 1/4 of. But yes, thank you for the reminder. I'm winding down now. Thank you. And you can keep the reminders coming too if you think I'm drifting. But now here's my point. 3 people just remember that the cosine of 60 is a 1/2. I'm not saying you have to memorize that. I am proud of them. But here's the real issue, or here's the real reason I asked. They are strictly correct. Strictly. If I wanted to be technical and tweak any details of what they were saying, there's no details that I could tweak. When Madonna and Yechan and Carla said 0.5 or 1/2, they're strictly correct. Meaning, notice this, please. Like, I never noticed this before until I did. They didn't say 1/2 meters. They didn't say 1/2 kilograms. And they didn't say 1/2 radians or degrees. They just said 1/2. And they're correct. Cosine spits out raw, pure, dimensionless numbers. They're literally correct. When you put something in, when you put radians into the cosine function, what comes out is unitless. That's why I wrote that with the square brackets down here. So that means, this is why there's got to be, like, if I'm thinking about units in science now, the answer that we're looking for here ultimately isn't X equals cosine of omega t. That's not good enough, because that would mean that all of the X values that ever come out wouldn't be positions measured in meters. They would just be numbers between 1 and -1. We don't want that. We want whatever comes out of the cosine, whatever number comes out of the cosine between 1 and -1, to, first of all, be multiplied by something in meters. And second of all, what do we want it to range between? We don't want the highest like, if you look at your mass on the spring in this problem in homework 1, the mass on the spring does not go back and forth between the raw number 1 and the raw number -1. It goes back and forth between 0.15 meters and -0.15 meters, right? So what I'm, to cut to the chase, since someone warned me, what has to go here, hence, I'm saying, hence, we need something measured in meters to multiply the cosine. And we need x to equal x0 when t equals 0, like back to the Madonna point and the Yachon point from before. We need it so that when t equals 0, the maximum value, the place where this mass is, where the place where the mass is, we don't want it to be the number 1. We want it to be 0.15 meters or whatever x0 is. The initial value of this whole thing is supposed to literally be the initial value of this whole thing. So look, what we're saying is we want our function to be x equals x0 times cosine of omega t, right? Think about it. When t equals 0, cosine of omega, whatever omega is, I don't care. You multiply 0 by omega, you get 0. Cosine of 0 equals 1. x0 times 1 equals x0, measured in meters, right? So I'm saying, just by thinking about units and transferring this raw math to measurable science, we start with the idea that the shape is the cosine shape, but then we added details to accommodate measurements. And now what we're saying is our function should look something like this. And it does, like that's our answer, okay? I mean, we're still not done like talking about everything, but that's what we have so far. I'm just looking at the chat. Yeah, it's almost, okay. Okay, thank you. Yes, it's almost 4:33. I still have 12 minutes, so you can keep doing that. I appreciate it. I'm going to take these 12 minutes, but yes, absolutely. And we're almost there too, but I appreciate it. So the only question left is, so, but that, oh, well, so we're almost at a point now. Are we ready to plug in numbers, to plug in t equals 1 to the above and spit out x? Like we're almost done. We've almost done all our work to establish. And again, we're trying to do all this to answer the last question of homework 1, but really it's our answer for all time. Like, how do we predict the motion of a mass on an oscillating spring? So this is our answer. The only thing is I still can't quite plug in numbers yet because I don't know. I know what x0 is, but do I know what omega is? Like, what is omega? So that's the last thing in the 10 minutes that I have left. Okay, what we mean by omega, let's look at its units again. The units of omega, okay, so, well, the units of omega are radians per second. So radians per second, it's sort of like V is meters per second. Omega is some kind of rate. It's a rate. It's like a speed, like velocity. Velocity is meters per second. It's how many meters you pass in time. Omega is not how many meters you travel through in time. It's how many radians you travel through in time. Okay. What I'm saying is, and I am watching the time, I do appreciate it. I still have 8 minutes. I am totally watching. And also, if I go a minute over 4:45 or something, that's on me. That's my problem. Like, I promise you're going very early, but bear with. If I go like a couple minutes over 4:45, that's my problem. But stay with me, okay? I promise you're going like an hour early. So but I do appreciate the reminders. I'm not saying that, but just don't leave before I do, please. Okay, today. So the real question is, I'm saying what omega is a rate of radian travel. But what is that? How does that mean? I mean, like, it's not meters per second. The thing is just going back and forth in a straight line. What does a radian have to do with the straight line? What is a radian? A radian is a measure of angle. Okay, and what is an angle? What is an angle? An angle, the most important, best way ever to think of what an angle is not an intersection of two lines. That's what I used to think it is. You could draw it that way, but that's not what an angle is. What an angle is a portion, a fraction of a circle. That's what an angle is. And that's like possibly the most important thing I can tell you, like, ever, or certainly today. An angle is a fraction of a circle. What I mean by that is everybody in this room knows what a right angle is, right? Whether you call a right angle, or, and please, like, think right angle. A right angle is the best example of what I'm saying. It's not the only, it's just the best. A right angle, you can call it a right angle, or you can call it 90-degree angle, or you can call it pi over 2 radians. It doesn't matter what you call it. We all recognize it when we see it. What is it that we're recognizing? We're recognizing a quarter of a circle, if you think about it. A right angle is a right angle because it's not all the way around a circle, and it's not halfway around a circle. It's a quarter of a way around a circle. That's literally what a right angle is, right? And it is a right angle no matter how long the lines are that you make, no matter how big the circle is. A quarter of a circle is what we call a right angle, and a half circle is what we call 180 degrees. Or a full circle is what my 9-year-old son, who plays too much Fortnite, calls 360 no scope. You know what I'm saying? Like, even my son knows what an angle is because he knows it's he doesn't think about it this way, but angles are portions of circles, right? So what an angle really is then is a portion of a cycle. Bottom line, I know I have like 3 minutes, but I'm going to say angles are portions of circles. You can measure them in in degrees. You could measure them in other languages, or you could measure them in radians. When you measure them in radians, what a radian is the most direct, literal way to measure the portion of a circle. It's just how it's arc length. It's like how much crust of the pizza you're cutting out per how big the pizza pie is, right? In other words, you know that the circumference around a full circle, I'm just about done, I promise, but I'm just about done. A full circle, you know the circumference around a full circle is 2 pi r. If you go around a full circle and divide that by the radius of the full circle, you get 2 pi. Right? So what I'm saying from here on in, is if you're ever asking, and I swear I'm going to, I still have 4 minutes actually. First of all, I'm saying an angle is a fraction of a circle. When you say something is a bigger angle than another, you're saying it's a bigger fraction of a circle, which ultimately in physics means a bigger fraction of a cycle. Specifically, to measure that in radians, the one thing to memorize or take away or realize is that to go around a full circle, what my son would call a 360 no scope, what we call in math is 2 pi radians. I'm literally saying 2 pi radians. By definition, a radian by definition is the thing that 2 pi of them make a full circle, or in other words, a full cycle. So from now on, and you know, pi is approximately 3.14, right? So just to give you an intuitive, approximate sense, and we're just about done, I swear. If 2 pi radians equals a full cycle, then that means exactly equals a full cycle, like by definition, then that means 6 radians approximately equals a full cycle. That means if I ever am wondering what the heck is a radian, but really, what is a radian? Yeah, I'm like, I don't get it. What a radian is approximately is a 1/6 of a cycle. That is literally what a rate from now on. If anybody says radian, what you picture is a 1/6 of a cycle, like approximately 60 degrees, if you want to think of it that way. But we're now in physics, so I don't even care about degrees. When we say omega is measuring, and I know I'm watching the clock, I promise. When we say that omega is measured in radians per second, what we're really saying is omega is measuring the rate at which the thing's going back and forth and back and forth. To go there and back would be 1 full cycle. To go there and back would be 2 pi radians, approximately 6 radians, right? Just because the circumference of a circle is 2 pi r. So to go there and back from here on in would be known as 2 pi radians. Therefore, a radian, if I say this omega has, if I say this oscillator has a omega, which from now on, omega, I'm going to call angular frequency. It's the frequency with which you sweep through angles. Where are the angles? There's no angles. I'm not turning. I'm going straight back and forth. But by angle, I mean portions of cycles. So from now on, if I say something has an angular frequency of 2 radians per second, what I'm really saying is it's going like 2/6 of a cycle per second. I'm saying it's making about 1/3 of a cycle per second. A radian is a 6 approximately, but that's just to give you a sense. A radian technically is 1/2pi of a cycle. But if you're trying to picture things, a radian is a 1/6 of a cycle. So when we measure omega, or talk about omega, it's what we're talking about is how many 1/6 of a cycle does this thing complete per second. And why 6? Because it comes from pi. Why pi? Because we're using the math that we already know about circles to graft on to the physics that we need for cycles. That's what's going on here. And last thing, I'm just going to write this, and I'm putting down the gun and taking the cannoli. I'm putting down the pen in 1 second. I'm saying for a mass on a spring, I'm just going to assert this. I mean, I think you established this in lab. We'll talk more about it next time, but just so you have it for the homework, and I'm done in 1 second. For a mass on a spring, what determines the omega is literally the spring constant divided by the mass. I didn't prove that just now. I'm just saying it. But how could I establish it if we had more time? How would I have figured that out? I would have done unit manipulation just like we just did to get the other stuff. I would have realized the units of K are newtons per meter, and the units of mass are kilograms, and the kilograms cancel out, and it works out to be the units that it needs to be for this. But that is the takeaway. I'm stopping. I'm putting down the cannoli, if you get that, or I'm putting down the gun. Hold on, I'm looking. Can I just get, I'm done. I know that I rushed that, but we actually just covered a lot more. Like, often it takes me the full class to do that. So I may or may not post a video. We're not behind. I might, but can I just get confirmation? What I just said, is it pretty clear? Like, do you basically understand what I'm saying? Thank you, Caitlin. Thank you, Mira. Thank you, Roland. Thank you, Carla. Awesome. Okay. Thank you, Ali Rot. Thank you. Okay. I know you were being polite, but cool. Okay. If it basically more or less makes sense, I know I still have much of homework 2 to go over, but again, you have 2 weeks to do the next one. So we'll see. Okay, cool. So if you're good, I'm good. Please have a lovely weekend and I'll see you next week. And thank you for being so flexible. Thank you. Yes, have a good one too. Thank you. And thank you for being here. And I will upload these notes, of course, right now. Thank you. And I will upload the video, obviously. Thank you, guys. Have a good day. Awesome. And I'm here for a second if anybody has a quick question or anything, but only say, oh, hello, Sebastian. Oh, okay. Goodbye. Okay.
Professor, I have a quick question.
Yes.
So, doing the homework that was due today,
Yes.
some of the questions, it was a little difficult to do the 5-step method.
Yes, that is true. Good point. Yeah, fair enough. No, I'm sort of worried about that. No, you're absolutely right. And I will not be rigid. You're right. And I want to tweak those questions for that reason, but you're right. And I will not be rigid when I look at it for that. Yeah, you're right.
Okay, perfect. Thank you so much.
Thank you. Thank you. Good to see you. Okay, bye.
Yeah.
Oh, and by the way, Josh, as long as did this little thing about relating radians of circle to does it honestly make sense to you, like this radian thing? Like,
Yeah, it was a bit of a review for me, so it was good.
okay, cool. All
That
right.
was good. Thank you so much.
Thank you. Okay, bye.
Bye bye.
Okay, bye. And Angela and Taco Rub, you guys good? Or you, yeah? Oh, Taco Rub, you good?
Professor, I just had one quick question.
Yes.
So 2 pi is equal to 1 cycle.
Good.
Right?
Yes.
So, and a hertz is equal to 1 cycle per second.
Good. Yes. Very good.
I just wanted to confirm that.
Oh, that's great. No, good for you. Yes. Therefore, as long as you're saying that, the thing we would have done next or whatever, you're absolutely right. Therefore, we can always say that omega equals 2 pi times f, like angular frequency always equals 2 pi times standard frequency measured in hertz. You're absolutely right. That's awesome. Yes.
Okay, I just wanted to confirm that.
Oh, that's good. Very good question. Yeah, you're absolutely right. Good job. Awesome. Okay, so I will.
All right, thank you, Professor.
Thank you. Have a great week. Okay, thank you.